All right, here let's look at a few examples of the infinity minus infinity form. So anytime you get infinity minus infinity, chances are it'll be two fractions, right? One fraction minus another fraction, or one function minus another function, and they both go off to infinity somehow. So if possible, if you can write the difference as a single fraction, that's usually a reasonable first thing to try. That's not always going to work. There might not always be fractions present, so you might have to rewrite it so that there are fractions present. But anyway, we'll look at an example of that next. But here's the difference of two fractions. When I let x go to 0 from the right, this thing is going to give me a positive infinity. And as x goes to 0 from the right, the denominator will go to 0 from the right. So here again, I get positive infinity. So this thing does have the form infinity minus infinity. So why don't I try to combine these two fractions using the old bow tie method, or common, whatever, least common multiple, whatever you're comfortable with. So to write this as a single fraction, so it's 1 times e to the x minus 1, which is just e to the x minus 1, and then minus x. So minus x. I just rewrote the order a little bit. And then I want to divide by the product of these two things. So x times e to the x, and then minus x times 1, which is just x. So now this was infinity minus infinity. Now if you plug in 0, right, you get e to the 0, which is a 1. Here you get a 0, so it's 1 minus 0 minus 1, that's 0, and then certainly in the denominator I will get a 0. So now this has the old form 0 over 0. That means we're allowed to apply L'Hopital's rule. So let me take the derivative of the numerator, right? The derivative of e to the x is e to the x, and then the derivative of x is just a 1, so I get e to the x minus 1. Certainly the derivative of negative 1 is 0. And in the denominator, I will need to use the product rule, right? So it's the derivative of the first thing, which is 1, times the second thing, so just e to the x, plus the first thing, which is x, times the derivative of the second thing. So again, that's e to the x. And then minus the derivative of x, that's just minus 1. So again, if you try to plug in 0, you get a 0 in the numerator. And then when I plug in 0 in the denominator, I get e to the 0 plus 0 minus 1. So again, that's going to be 0. So again, I get the form 0 over 0. That means we can apply L'Hopital's rule one more time. So in the numerator, I get an e to the x, right? And in the denominator, I get e to the x. And then I need to use the product rule again. So again, the derivative of x times e to the x is just e to the x, and then plus the first thing times the derivative of the second thing, so x times e to the x. So that's good. So now let me combine some like terms in the denominator here, right? So I've got 2 times e to the x plus x times e to the x. And now look, we've got an e to the x in the numerator, and we've got an e to the x that we can factor out in the denominator. So those e to the x's will cancel, and I'm left with 1 over 2 plus x. So that's nice. Now you can plug 0 in for this thing, and you just get 1/2. So that would be a good final answer for this exercise. All right, here's an example of an infinity over infinity where there aren't any fractions visible. So we need to sort of insert some fractions somehow. And if anyone sees an easier way to do this problem, please let me know. I'm not sure this is the most straightforward way to approach this, but it's the only way I could see how to do it. And I did spend some time trying to figure it out. It's of the form infinity minus infinity. Again, there are no fractions available. So what I'm going to do is to factor out an x. Right, so when I factor an x out of x, I'm left with a 1. And when I divide or factor out this x cubed plus 1 to the 1/3 power, I'm just left with the same thing and then over x. Okay, so now it's of the form infinity and then times 0. Again, if you let this part go to infinity, the leading coefficients are just 1 over 1. And so the limit here is just going to be a 1, if you remember how to write down limits as x goes to infinity. So here I'm going to get infinity times 0. So again, we can still apply L'Hopital's rule to this. So if I get an infinity times 0, the thing is to write the flip of one of the things in the denominator. So instead of multiplying by x, I'm going to divide by 1 over x. And so in the numerator, I just get 1 minus x cubed plus 1 quantity 1/3 over x. In the denominator, I get 1 over x. So we don't want to take derivatives of these expressions, right? Too many fractions. That doesn't look like an easy task, right, with the chain rule and the quotient rule or logarithmic differentiation or whatever. So let u equal 1 over x. That'll get rid of some of these fractions. So remember, if I let u equal 1 over x, what happens to u as x goes to infinity? Well, u goes to 0 from the right as x goes to positive infinity. So this limit as x approaches infinity now becomes a limit as u approaches 0. And so how do we write this thing? Well, certainly 1 over x is just u. That's what we said. And now to multiply by 1 over x is the same thing as to multiply by u. And now x cubed, well, x is the same thing as, right, x is the same thing as 1 over u. And so x cubed then is 1 over u cubed. So I get u from this 1 over x out here. And then in the parentheses, I get 1 over u cubed plus 1, and then raise that to the 1/3 power. So make sure you're good on how I got from here to here. Now this is a much easier thing to deal with. So now in the parentheses here, I want to try to simplify that thing a little further. I can do that if I factor out a 1 over u cubed from both of these things, and you'll see why I'm going to do that in a minute. So when I factor out a 1 over u cubed from 1 over u cubed, I'm just left with a 1. And when I factor a 1 over u cubed away from 1, I'm left with u cubed. You can see if I multiply 1 over u cubed by 1, I get 1 over u cubed. And if I multiply 1 over u cubed times u cubed, I just get a 1. So make sure you're good on how I got from here to here. Make sure you believe that these two things say the same thing. Okay, now, the 1/3 power of 1 over u cubed is just u, or sorry, 1 over u. And so here I get u times 1 over u, and so these two things are just going to cancel. So now I'm left with 1 minus 1 plus u cubed to the 1/3 power over u. This is a much easier thing to differentiate than any one of these other things, right? It's a basic fraction over, right, a basic numerator over a basic denominator. And so now we can apply L'Hopital's rule, right? As u goes to 0, this thing is going to go to the 1/3 power of 1, which is just 1. So I get 1 minus 1, and then which is 0. And then in the denominator, I get 0. So now we can apply L'Hopital's rule to this thing. Okay, so we have gone through great pains to rewrite this function as a fraction. And so the limit as x goes to infinity of x minus the quantity x cubed plus 1 to the 1/3 power can be rewritten as the limit as u goes to 0 from the right of 1 minus the quantity 1 plus u cubed raised to the 1/3 power, and then divided all of that divided by u. So we've switched this thing from an infinity minus infinity form to a 0 over 0 form. So now we can apply L'Hopital's rule. So the derivative of the top, it's just 0, and then bring the 1/3 down in front. So negative 1/3, recopy the inside, and then take 1 away from the power. And then tack on the derivative of the thing in the parentheses. And then the derivative of the denominator is just a 1. So really, this limit, according to L'Hopital's rule, is just the limit as u goes to 0, negative 1/3, 1 plus u cubed to the negative 2/3 times 3u squared over 1. And so the 3's will cancel, and you can write 1 plus u cubed to the negative 2/3 as positive 2/3 exponent in the denominator. And so really this is just negative u squared over 1 plus u cubed raised to the 2/3 power. I can certainly plug a 0 into this thing, right? And so I get 0 over 1 plus 0 to the 2/3 power. So that's 0 over 1, and that certainly is just 0. So that would be a good final answer for this problem. Okay.